Hi there. So we've just discussed what it means for x to be a stationary point of a function in one dimension. Now we want to investigate what we mean by a stationary point of a function of two variables, just to generalize a little bit more. So the best way again is with a diagram. So I'm going to draw some coordinate axes. So this is going to be our z-axis, this is our x-axis, excuse me, our y-axis, and this is our x-axis. So this is our x-axis, this is our y-axis, and this is our z-axis. And suppose we have a function looking something like this, and we can see our stationary point is somewhere here. So somewhere here, let me just plonk that there, and we start at our point there. Now, suppose what happens is we move a little bit along the x-axis by an amount h. So we started off at our point x, and we move to our point x plus hx, and we move along the y-axis from y to a nearby point y plus hy. Well, we want to work out where on our function of two variables we're going to land, and I think it's going to look something like this. So just a little bit higher because it's further out, and this is kind of some kind of bowl, so it's going to come further out. Well, what happens is, if we just try to be a bit careful about how we're drawing this, again, the function is going to change, and it's going to change by an amount here, delta f. And again, we have a similar pattern to before. We started here at a point with coordinates x and y, and x, we moved from x to a near to by an amount h to x plus h, and we moved away in y by an amount y plus h, and of course that's hx and hy. And so we moved in the xy plane, and as a consequence, f of x and y changed to f of x and y plus delta f. And now again, we're in a position to define carefully what we mean by a stationary point of a function of two variables. So what we mean is that our delta f, which we can see is just, and again looking back at the axis, we have this point here, which is our know it's getting a bit busy, but please try to bear with me. That's f of x and y, and this is our displaced point on the z-axis, f of x plus hx and y plus hy. And now delta f is of course the difference between those two, so it's going to be f of x plus hx and y plus hy, and we subtract f of x and y, and this has to vanish for small displacements hx and hy to first order. And of course, again, this is what we mean by a stationary point. So this is the same as saying that the point x, y is a stationary point of f. And worth boxing up because this is our definition of a stationary point in two dimensions. Now again, we just follow the same procedure from before. We expand out that delta f by first investigating f of x plus hx and y plus hy. Well, we can use Taylor's theorem in 2 dimensions to expand this into f of x and y plus hx times this time the partial derivative of f with respect to x plus hy times the partial derivative of f with respect to y, and then we're left with higher order terms in hx and hy. But we have a nice way to write that for higher order displacements. We simply write big O of the modulus of hx squared plus hy squared. So big O times the modulus of the displacement. And these again, this just encompasses any terms that have any contribution of higher order than hx squared and hy squared, and including terms of order hx squared and hy squared. And now we play the same game we played before, so we write delta f is just our f of x plus hx and y plus hy minus f of x and y. And to be clear, this came from here and this came from here. Well, all we have is what's left over on the right hand side. So we have hx, the partial derivative of f with respect to x, plus hy times the partial derivative of f with respect to y, and of course our higher order terms in hx squared and hy squared. So this is big O of mod hx squared plus hy squared. And again, these displacements here are small, but critically not zero. Absolutely not zero. They are finite, but as small as we'd like them to be. And these, we treat them as negligible, so we treat them as if they were zero. So for delta f to vanish to first order in hx and hy, we require that df dx is equal to df dy is equal to 0. And this is what we mean by a stationary point of f. So point x, y is a stationary point of the function f. And this is worth boxing up because this is our careful definition of what we mean by a stationary point. Now we can do a bit better. If we put those two together. So we're kind of saying that one object is 0 because we know that actually this is the same as saying that the gradient of f, which is just of course df dx times the unit vector in the x direction plus df dy times the unit vector in the y direction, that's just equal to the 0 vector. So really, we're just saying that the gradient of f vanishes. So this here is the same as saying that the gradient vanishes. We're saying the gradient of f is equal to the 0 vector.